So, welcome to the detection decisions module of dynamic field theory. So, part of the core lectures. And I remind you first where we ended last week, which was really identifying the neural dynamics, the differential equation, integral differential equation that governs neural fields and that has peaks as stable states, attractor states from intrafield interaction. Remember, the notion was that neighboring sites in the field are coupled excitatorily. So the coupling strength between those locations, when X is close to X prime, two locations are close to each other. Around here, there will be a positive coupling strength. So neighboring locations excite each other. While when the locations are further from each other, like beyond here, so same on, no matter which side you're on, have a negative coupling strength that will be inhibitory connections. And so if you have a localized piece of activation, it would suppress activation at locations further from the location you're looking at, and it would excite locations that are close to where that activation is. And that's how peaks can be stabilized against decay by this local excitation. And if you only had that, then there would be a risk that the peak would grow because it always excites its boundary and could diffuse, become broad. And you can actually in the simulator play with that and find regimes where it does that. And that is something that is limited by inhibitory interaction. So at some point, when the peak becomes broad enough, the excitation in the center of the peak will start to inhibit the side, the outer boundary of the field at the outer boundary of the peak when it gets into the inhibitory regime, and that would limit the growth of the peak. So that these two factors stabilize the peak. And it's critical for this form of stabilization that the dynamics is nonlinear. It becomes nonlinear through the sigmoid threshold, that is only activated locations contribute to the interaction. So for instance, when you've been able to suppress activation at another location where there is input, like this one, then that activation cannot in return inhibit the location you initially looked at, and we'll see that's the basis for selection decisions. So I have here a slide that summarizes the math of this field, and the book chapter we just I talked about before we started this recording reviews that mathematics. We call this the Amari equation because the mathematicians Amari analyzed this equation. It actually goes back to the so-called Wilson-Cowan model that was neuroanatomically justified, and we don't really give the derivation of that from the underlying neurophysics. So it's very much like the single neuron dynamics that you've looked at. So the rate of change of an activation variable is proportional, inversely proportional to the current level of activation, the minus U term. We've put here the tau on the left as a parameter that fixes the time scale on which things evolve. That's where there is no coefficient here in front of the minus U. So rather than have some strength of that slope, the slope is sort of controlled by the tau here on the left. The difference is that previously we had neuron number 1, neuron number 2. Now we have continuously many activation variables, and typically you write that down as U depending on as a function on some dimension X, rather than think of X as an index, a discrete index. It's a functional dependence. So U is a function of two things of this dimension X, which in these examples here is always just one dimension, one number. It could be, and we'll get that in the new year, we'll be looking at multidimensional fields when X is a vector, and it depends on time. So this is the minus U term, plus H, the constant negative resting level as in the past. The inputs are specific to every location. That's where the strength of the field picture comes from. As I discussed 2 lectures ago, the sensory surface ultimately determines what this field is about, what X means. It's the forward connectivity from the sensory surface that can determine that. And in the motor case, it's actually the projection onto the motor surface that determines that, but you'll have to understand how the activation patterns in the field arise to have the meaning that the forward connectivity has. And it really just means that the activation is a function, the input is a function of that index, and very typically we'll look at localized inputs. There's inputs around a particular value of x that will be specifying peaks, and peaks will represent particular values along the dimension. So this is just straightforward from what you've seen before, right? Exactly the same equation, except that where we had u1 and u2, now you have a u depending on x, a functional description. Differences here in the interaction. Previously, you have seen self-excitation, where there would be some coefficient w, and then the sigmoid applied to the same field variable. We had u of 1 or u, just u. Now we have and yet competitive or inhibitory coupling, where you had minus a constant times the sigmoid applied to the other activation variable u2 when you're looking at u1. And this combines these two into one. That is, here you have an integral which is just a continuous form of a sum over all other locations dx prime. If x is the location I'm looking at, all other locations dx prime. And every location contributes to the extent to which it is above threshold. So if you at location x prime is sufficiently positive, then the sigmoid returns a positive value and there will be some contribution. If the activation at that other location x prime is sufficiently negative, then the sigmoid does not return any value and you don't contribute to the integral. And then the sign and strength of that contribution is determined by this so-called kernel. And the assumption here is that's homogeneous. That is, the strength of contribution depends only on the distance between the location we're looking at, x, and the location x prime that we're summing over. So when that x is close to x prime, that's what I was just saying, this integration kernel will return a positive value. Here in this concrete model, it's a Gaussian positive value. So this positive part here is a Gaussian, but it could be other functions that you could choose here, has certain width. So when x is close to x prime, this will be a relatively small number. An exponential of minus a small number is something, not zero. So it's, let's say if it's 0, then exponential of minus 0 is 1. So there you would have the maximum here of this exponential function being 1. And therefore then this weight WE, which is a positive number, would predominate. So this will be a negative number and the absolute value of this is larger than that. So you would have overall a positive number. And so for x close to x prime, this will be a positive number and there will be excitatory coupling, positive contribution to the rate of change. If you're looking at distances x prime or locations x prime that are far from the location you're looking at, so this is a large distance, then this factor has decayed, and therefore only this coefficient here would remain, and we arrange for that to be a negative number. So in this picture, this distance here, that will be the WI, the inhibitory contribution, is a negative number. And in fact, the excitatory level that is here from this level all the way to the top, that will be the excitatory level. And so we make sure that that is a larger positive number than this is as a negative number. This is a specific kernel, the kernel in which inhibition is constant, as we say, that is, at all distances you have the same inhibition. In this formula, this does not depend on x. That's not the most general form. We're also sometimes considering inhibition that falls off at large distances, so that locations that are really far from each other don't interact anymore. So it's also a Gaussian function, but with a larger sigma. And in the simulators that I'll show you, you have a term for that form of nonlinearity. It's also discussed in the book chapter, but here I gloss over it. We always use the same form of the sigmoid, so-called Boltzmann form, where the threshold is 0 in our case. But actually nothing really rides on that. You can use other kinds of sigmoids. I'm not going into that very much here today. So that's the mathematics of that. You don't really need to understand the mathematics very deeply. It is strongly analogous to the discrete case, and you just have to understand somehow replacing the sum of terms by an integral. An integral is really just, again, is a continuous form of summing. I hope that that's not too much of a challenge. I have here a slide that explains this particular notion of convolution. So this integral is sometimes called the convolutional integral, in the sense that the first function is a function of a distance between the outer variable, an outer variable and the integration variable x prime, and then the second depends only on x prime. And so those who are not familiar with that, just make it concrete. Let's say if this is the field, this is the space we're looking at, we have, let's say, 180 degrees. This comes from an angular notion where x would be an angle, 180 degrees. And this would be your kernel. So the kernel is centered around, it's a function of distance in the field, so centered around 0. And the notion would be that you apply this kernel to any location. So for instance, if I'm looking at what would happen, what is x dot at, let's say, x equals 50, then to do that, I would have to center this kernel on this location that I'm looking at. On this location I'm looking at, and then multiply. So here at the bottom, you see this blue kernel is multiplied with this function. This function is the sigma applied to the field, so it's a positive number. So the red and the blue are multiplied, and when you multiply the red and blue, you get that black number, right? Anywhere where one of the two is 0, you get 0. So only where the red goes away from 0 do you have anything in the black. And then you see here is largely positive, and here's a little bit negative from the negative part of the kernel. So you get the black number. So there will be this right-hand side at one particular location, x, which was 50 here in this particular case. And so the black curve here, right? And now you have to think of that. You would be picking up that number as a contribution to the rate of change at x equals 50. So that gives an input to x dot to u dot at that location. And now if you look at another location, you would have to shift this kernel to apply to the next other location. And yeah, for every location, this here is centered around a different point in the field. Now, at any given location, what you do then is you sum over the entire field. So you integrate over all the x prime that you have taken input from. So here there will be in this finite field would be from -90 to +90. The original space is 180. So if you look at all the distances, the maximal distance from the center, is -80 to +80. So you're integrating over this black line, summing everything over this black line. See, there's very little negative, and there's a little bit positive, and most of it doesn't contribute at all. And that integral, the integral is the area under this curve where you take the sign into account. So you would get this area here and a little bit negative here. That is one of the contributions here of this term on the right-hand side. And that would be for one particular x, and then you do that for other x. You see that a problem that arises is that when you sum like that, you might be running into values of the underlying field that are outside your range. If you center this kernel on some location here close to the boundary, the integral extends into values you don't have. And this is a well-known problem in convolution. And the idea is that you expand the space to make that integration possible. So for instance, here you glue to the left side of the field, you glue a copy of the right side of the field. So a copy of from 90 to 180 is glued here to the left, and here on the right, a copy of the field from 0 to 90 is glued on the right. And you take that, copied stuff from the other side into account in the integral. This amounts to essentially considering the field a periodic thing, that you're as if it was closed on a circle, and your kernel would be extending around the circle. Still, that's not supposed to matter, because your field might not really be of that nature. It's not necessarily a periodic space. For instance, here 180 degrees is not the full circle, so it's not necessarily what you physically want to do. And so what you have to make sure is that you don't get close enough for that really to matter for what happens on the boundaries. So this mathematical trick, the padding, is a way to make this system not sensitive to what happens on the boundaries. So this is technicality. You don't need to understand. I just said this for those who know what convolution is to understand this particular problem. The code that we make available through the webpage or MATLAB or CDAR all takes care of that. You don't have to look into the details of that. Good. So last week I went to the simulator, and I want to do that again. And I have to change my screen sharing for that. I should have thought of that. Do this sharing here. So actually, I also make a mistake here in that I'm showing. I have to pin my video and only show myself, I think. If not, this will be perhaps your faces will be seen on the video. I'm not sure about that. You remember on our webpage under learning, we have access to the simulators, the two neuron you already used. And last week we talked about the simulator that does fields, one layer field, that shows the field in blue here on top, the fluctuating thing. There's a little bit of noise here that I can change in strength. That is visible here. Behind the blue is the input corrected for the resting level. So it's -5 here because the resting level is set to -5 and there's no input currently. And then the solution that you have is the field equals to the resting level. So if you go back to the slides here, you see that the attractor state is u dot equals 0. If this is 0 here, then you can add u, so to put it on the other side, and then u is equal to h plus s. If this doesn't contribute because the entire field is negative, h plus s is really the fixed point, and therefore in this simulator, when no location of the field goes above 0, then blue is equal to green because the field is equal to h plus s. And here I'll show you, you can put little inputs here, and you see as I add little Gaussian inputs, the blue tracks the green with some delay because it's going to the attractor, which is always the blue equals to the green. The red curve up here is the sigmoid. So when I increase this enough, you'll see something is going to come up. This is the sigmoid applied to the blue, to the activation trace with a relatively steep threshold. So this is actually no interaction going. I've turned off interaction. So here, all you see is that where activation is positive, the sigmoid returns a non-zero value. On bottom, you see the interaction kernel. The interaction kernel is centered around 0. So here is the center. This is a function of distance, left and right. Currently, it's 0. They're different. You can actually yourself organize the interaction kernel. So for instance, put a local excitation here, put a global inhibition is what I just did. So there's a negative value and a positive value here. You can also make this Gaussian form of a regional letter inhibition. This is a possible kernel. There are actually kernels here that you can load that are stored. So this is, for instance, a nice kernel for selection. Actually, for detection, we can try this here. Oh no, I want the selection one because that's the one I explained. So that just sets these parameters to the values that are indicated by this kernel function shown here. So that's just to explain the simulator, and you all have access to that simulator going to that webpage. You can play with that simulator. Maybe it's difficult to do that right now, but you can do that as part of the exercises. I'll ask you to do that, but also just for fun. Now here on the right, you have buttons that control inputs. These inputs are just in the simulator, just Gaussian functions that we just put there to make it convenient. And they're each has 3 parameters, namely the width of that input, where it is in the field, initially set to be sort of equidistant, sort of staggered, one at 25, one here in the middle at 50, and the third one at 75 here on the right, but you can change that. And then the amplitude, they're all off, and you can increase. You see them. You see the green curve is a Gaussian. If you make it narrower, it's maybe more obvious, right? And you can also make them very, very broad. Yeah, I can play with that. Okay, I want to go back to this value. So now I'll demonstrate to you the detection instability. I said it last time. That will be the instability at which this green solution, where blue is equal to green, where activation just equals to the resting level plus input, where that solution becomes unstable. That happens when that solution approaches 0 right here, and it becomes unstable. See, now the system moved away due to noise from the case where the blue was on top of the green to a new solution. And this is what we call the self-stabilized peak or self-excited peak. And self-excited quite literally because there is excitation here, positive activation in the peak that exceeds the activation that is put in by input. So here you have a positive gap activation higher than input. That's through different sites within the field exciting each other. And that positive excitation is exactly in that region where activation is positive. So this runs into some kind of self-consistent loop that determines the size of the peak. While beyond this region where positive activation is self-excitatory, this region here inhibits all the other locations because I chose this kernel where inhibition is constant. All the locations are equally inhibited, so they're all at a lower level of activation compared to the input. So, for instance, if I reduce the global inhibition in strength, you see then this is less. If I increase this, oops, sorry, it's more. So you can see how the peak depends on the size of the activation. Similar, if I make the excitatory peak larger or smaller, it changes how much self-excitation there is. That changes the amplitude of the peak and also the width indirectly. Just resetting the kernel. So I said that it's an instability, and that can be demonstrated by saying that if I'm at the other solution, I'm running away, and there you see I'm running away from that solution. So clearly no longer stable. This little noise helps to destabilize the peak. I can reduce the noise to 0. Now you see, even without noise, I'm just above the instability, so it really doesn't stay below. Somewhere here is the limit. Now it's still stable, so it will stay. If I just add a little bit, it becomes unstable. Yeah, so this is clearly the limit of stability. If I consider the amplitude of this localized input, the parameter, this is the limit of stability. Beyond that, this is not a stable state anymore. So the other thing is that this solution that it goes to is a solution that has been around. It's really the subthreshold solution that is unstable, and the system then runs somewhere else and has that self-excited state. But that's a self-excited state. It doesn't come about at this location. It has been around for a while, meaning at lower parameter values. And I can demonstrate that, as I did last week, by lowering the input to a state where there is now there is still a solution, a subthreshold solution. I'll demonstrate that in a moment. And you see that the peak persists. So in this region, a peak, a positive excitation, peak of activation is a stable state. I can add noise just to make it obvious that it's really stable. Yeah, so that does exist, even though the other solution also exists. By resetting to the resting level, I can demonstrate there is also this other solution. So in other words, this is a bistable regime where the field can be in either state, and which state it is in just depends on the prior history of activation. So if it was previously off, this is what I'll get. It will be tracking this until I hit the instability. Then the system becomes monostable, only this solution exists. And if I go back, I see the bistable regime. This bistable regime has its limit also on the lower end. So if I lower input enough for this amplitude, not enough excitation being left, then the peak becomes unstable. So now system is monostable, has only this off solution. So go back and somewhere it happens somewhere around here. For instance, this is still stable, 3.6, and then somewhere here, maybe a little less, where it becomes unstable. I have zero noise here, so this is clearly in the unstable range. So this is the detection instability that I will be now discussing in more length, the meaning of it in more length in the rest of the lecture. I'll just use this occasion to point out two other things that are important about that. I already, I think, indicated that last week that you can go through the detection instability in multiple ways. For instance, I could have these small inputs here and could now shift the system through the detection instability by, oops, I went, no, I can't go there, right? Sorry, I have to redo this. Don't know why that happened. So I'm just adding here. My touchpad is very sensitive, unfortunately. So I put these little Gaussian inputs here, and now I'm adding a boost. Let's turn, no, I need a little noise for this. A boost, pushing this up. And if I do this enough, somewhere activation can become positive, like here, and then a self-stabilized peak forms. And you see the self-stabilized peak is sort of the same as when I induce the peak by localized activation. From the point of view of the field, it creates this extra activation by self-excitation. It in the peak, remember in the previous condition, actually, let's go back to the resting level we had, the -5, and induce a peak in the localized, through localized input. So we said, in detection instability occurs somewhere here, like right here. And see, most of the activation in the peak is really due to interaction. It's this self-excitation. Everything above 0 is self-excitation because the input would just put the field here. And therefore you see the difference between this peak and the peak I was showing here, where the input is smaller, is really tiny. It was like this. And it was just based on boosting the field, right? Let's do that again. I'm just boosting the field, induce the peak. Oh, now it forms around the other location. See, the blue line, the activation peak, is pretty much the same. It's a very similar kind of peak. So if we think of the peak as a unit of representation, you can induce a peak like that without localized input that would be sizable or would be a major part of the activation in the peak. That's how the peaks, in a sense, are normalizing. They are generating activation distributions that depend little on input. They will depend a little bit on input, but not very much. For instance, if I add here at that third location more input, you see the peak is being reshaped a little bit, but not very much. It's sort of damping, much less than the input-driven solution was. So we call this form of inducing the detection instability, sometimes the boost-driven detection instability, becomes really important for things that we consider higher cognition, namely when categorical states are induced in fields and sequences of such states occur. For now, just want to, I'll come back to that much later in the lecture, like in January. But for now, I just want to drive home this point that these peaks that are self-excited are somewhat independent of how they came about. They are solutions that are largely dominated by interaction. Most of the activation here, in this case, is literally, there's very little input. Most of the activation here in the peak is really made from interaction, from excited interaction. And of course, the negative part here is also largely caused by inhibitor interaction. Last week, I made the point that this also leads to categorization, that the peaks will only arise at particular states where there is any minor inhomogeneity is amplified through these through the detection instability into macro states that then do not occur at every location in the field. And that will be also important when we look at higher cognition. Last point I want to make, actually the two more instabilities, but I'll study them separately over the next couple lectures, but I just want to remind you of these. If I go back to our default parameter values, that I can also understand how selection decisions are made. So if I have multiple locations at which I have input, then under these conditions, with a global inhibition, only one of those can support a peak and inhibits the field enough so that it cannot go through detection at the other locations. And then you can overcome that, for instance, like this, and then return to the original value. And therefore, you see that the field might be actually multiple stable selections, and which one wins is a question of initial condition or who rises first. And then I also hinted at last week already at the fact that you could have conditions, which I generate here with the arbitrary setting here, at which a peak persists just because just because of interaction. So I reduce all input to 0, and the peak exists. It's very close to the case we had with the homogeneous resting state. I did this here by making the resting level very high. And if I make the resting level lower, the system goes through the inverse detection instability. But that is not the only way to do it. For instance, I could just make excitator interaction larger, and then I can tolerate lower levels of input. For instance, the -5 that we had. This is even more than that. The -5 standard setting gives me a self-sustained sustained peak of activation without any localized input. If I just make the excitatory part of the kernel a little larger. If I make inhibition larger, so in this direction, then I can destroy that again. So these are the different dynamical states and their instabilities. And I can switch application to show you again to summarize again these different states. So when you have the input driven, we call this the sub-threshold solution, and increase localized input or global inputs, you run through the detection instability where this solution becomes unstable, and you come to the self-stabilized peak suprathreshold solution. Different names, we give the same thing. And if you take that input away, you can induce the reverse detection instability where you end up in the input-driven solution. And it doesn't have to be, it can be any kind of input. It can be a broad, boost-driven detection instability, means the input is broad, is, for instance, a constant input. It could be a neuron that projects onto all locations of the field equally, or it could be more or less localized. And the other two instabilities are the selection instability. So the capacity to select is a property of the field, and the selection instability is that the number of possible stable states varies as you introduce different input strings. So when one location gets much more input than another, then you go through an instability where only one or a small number of selections remain possible. And working memory is the interpretation of the self-sustained pattern. So without any localized input, a peak can be sustained under appropriate parameter conditions. And there's an instability connected to that, which is really the reverse detection instability for global parameters. So when the self-excited peak becomes unstable, all while localized input is 0, and then the sustained state goes away. So the capacity of the field to keep working memory goes away. So these different stable states and their instabilities are really what what is at work in dynamic field theory. So the next couple of lectures, in fact, the rest of the course just leverages always these same stable states and instability. So we'll always only be thinking about input-driven subthreshold versus self-stabilized suprathreshold solutions, and how to go from one to the other by making one unstable, then switch to the other, and the other way around. It's always these ultimately just three instabilities: the detection, selection, and the memory is a little less important. These three instabilities make every effect. So now I just want to expand on the detection instability a little bit to explain a little bit more its psychophysical underpinnings. This is a picture from the book that just summarizes that again. So I have small input, only suprathreshold solution, a little bit larger input. I might have two solutions, the subthreshold, but already the suprathreshold. And then at the upper limit, I have these subthreshold becomes unstable. This is where the detection instability occurs, and only the suprathreshold is present, and the self-excited peak might be then has a monostable regime. If I go back, the loss of the peak here is the lower limit of the bistable regime. So then you go to the monostable regime. So in this direction here, you go through the detection where the dashed line disappears, and in this direction you go through the reverse detection where the solid line disappears. So what does that mean? So one intuitive thing is we're saying it stabilizes decisions. It's detection decisions in the sense it's really only the transition from no activation or no significant activation that will be handed down to significant interaction, suprathreshold interaction. And we're not talking about here the detection being specific to one location versus another locations. That will be selection. We're just generically saying just anywhere in the field does activation arise that can have impact on downstream structures. Now, you might think the usual way we would think about such a detection decision is really just in terms of the sigmoid, of just saying, well, when activation goes beyond the threshold, then I transmit information downstream. In fact, many connections networks are using the sigmoid in that sense, sort of as a readout function to say, does my field, can I read out a choice from the field? Does it respond or not to this? Are those neurons on or not? Well, because we're looking at activation patterns as a function of time, because we're ultimately thinking, of course, of these fields as being used in closed loop in embodied systems, as I was suggesting in the introductory lecture. So for instance, somebody acting constantly in response to sensor input and moving around and making decisions, for instance, detecting a ball in order to then activate some behavior to orient to the ball, in that soccer example I was using. Because of that, we're always thinking of activation as evolving continuously in time. So there's always an activation state, and the activation state is subject to inputs from many other neurons in the brain. So it would be highly integrative. These neurons might do things that are unrelated to the current task, and we could consider them noise or perturbations, distractors, or they could be also just literally neural noise that is happening in the brain. And because of that, the idea of going through threshold is by itself not really a viable idea. So in any simple mathematical formalization of randomness, randomness really means that on different occasions there are different outcomes, and if you think of the underlying degrees of freedom, different neurons, for instance, being independent sources of noise, so statistically having some form of independence, there's a probabilistic concept of independence, then these different moments in time, you will have a decision to be above threshold or below threshold that isn't, in a sense, not very correlated. We can make this exact, but I'm not going there. It will be something, for instance, like a Wiener process for those who know these sort of things. And that makes that when you have a threshold piercing, there is a high probability that the activation will go below threshold again. In fact, if this is a linear process, Brownian noise. I just mentioned that for those who know these sort of things. You can prove mathematically that in the vicinity, meaning infinitesimal environment of any zero crossing of that Brownian motion process, there are infinitely many other zero crossings. That's this funny sort of thing that mathematicians can prove about such things. So in a sense, it's very generic that there would be a problem with threshold piercing. When you take threshold piercing as the decision making and you think of the underlying neural process of going on in time, then whenever you have a moment in time when you would make a decision, the next moment in time, you're very likely to undo that decision, fall back below, and then do it again, and so on. So that is certainly something that is not practical. That would be a system that revises its detection decision many times until it's moved far enough, let's say, from the threshold. And what the detection instability does, in a sense, is it makes a macroscopic shift. So if you plot where the stable state is, you might think that's sort of like a threshold, but it's not, because this is all activated states, and the threshold of the sigmoid would be here, and that's where you go through very steeply, because that's not actually a stable state. That is, here you're on a transient to go through the transition. In fact, we wouldn't say that anything rides on when you pierce the threshold. Everything rides on how much activation you have in your attractor state and you staying in that attractor state. For instance, let's say think of that activation ultimately impacting on your muscles and driving your muscles, and then it certainly takes some time for your muscles to generate any kind of movement. And the important thing for initiating the movement would be that the muscles get engaged long enough for you to really make the movement. And so that would be all dictated by you staying close to the activated state, being in that stable state. And it's not, even though in some models we might say, whenever activation becomes positive, then I will start, I will say that's the reaction time, let's say, and I will start counting. But the process is actually driven by the system going to a new attractor state. So this key concept is that we will be stabilizing the decision. We will suppress this for sort of doing and undoing the decision. So in the summer semester, I'm teaching about how this form of stabilizing decisions adds interesting functional features. For instance, engineers emulate that sort of thing when they use detection decisions in a statistical sense and stabilize such decisions through, for instance, hysteretic algorithms. And here I just want to point out that in the nervous system, we have evidence for such stabilization. So for the downstream macroscopic neural state persisting even as its input varies. And the key evidence for that is hysteresis. And I'll show that in a moment. Here is the slide I showed previously about hysteresis to point out that it also has a very interesting effect on the emergence of discrete events out of continuous time. So this is the slide that I showed in the context of just having two neurons, or not, a single neuron, self-excited neuron. This is from a simulation of a self-excited neuron, but the peak is sort of like the neural realization of that. And I pointed out that then if you had a continuously time-varying input, in this case it's an input ramp that with time ramps up input in a linear way, then at the detection instability, the activation starts to deviate from a linear function and switches to the off state in a somewhat abrupt fashion. So you could say this moment in time when the detection happens is a discrete event that emerges from an underlying continuous change. And actually, analogously, the reverse detection is a discrete or induces a discrete moment in time when a macroscopic change happens as you decrease the input strength linearly in time in this model. And we plotted time to the left here to align these two things. So that's an important role of the detection instability. That's why we make so much fuss about it. We take for granted in a lot of cases that there is the self-stabilization, even though we have to look at evidence for it. It's not much studied really because of some difficulties I'll point to in a moment. but it's very critical for how discrete events emerge from time continuous neural processing. And this is something that has been overlooked in some theoretical modeling, because a lot of the models are just tracking events. For instance, if you think of information processing kind of models, so that model the brain as a computer program that calls routines, and then when the routines are done, they return their value and so on. You see there, the discrete events are part of the language, because there is a discrete moment when you call the routine, and then the routine returns the value at a particular point when it's done computing. And so it seems as if there was nothing to explain about that. That's just in the nature of this thinking. But of course, in the brain, that's not the case. There isn't a computer that cycles away and then a function returns a value whenever it is done. In the brain, it's just a bunch of neurons that continuously update their activation states. And therefore, in the computer, in the brain, it's a real issue to understand how the system can end up making decisions at a particular point in time when the sensory motor basis on which it makes the decisions depends continuously on time. So this you will see in a lot of the rest of the course, and I'll make one particular presentation at the end of the course on how sequences are generated autonomously in neurodynamics, and they critically work on this kind of leverage the detection instability. Now, I wanted to go through two examples of empirical evidence for the self-stabilization of decisions that come from hysteresis. And I'll point to some difficulties of that. Now, hysteresis, so hysteresis is essentially that a change depends on the direction in which you go through, that you, when you increase a parameter, you will detect the change at a larger value than when you then decrease the value, you change back. So there's a regime where you have some kind of resistance to change, where you stick with the previous detection. And in that sense, hysteresis is very well known in psychophysics. So for instance, if you ask people to observe a particular something, detect maybe a strength or a signal or a radar signal, the classical thing, you have to detect an enemy warplane on your radar, and you will find that you need a good signal to make that detection. And once you have made that detection, you can actually track the enemy warplane on your radar screen, even when the signal now becomes weaker. But once you've made the detection, you're more likely to be able to keep it. And when you're losing it, then you're lost, and then you need more input to stabilize it again. So that's very close to what the dynamical account would talk about. Now, these kind of phenomena have been known since the early days of psychophysics, but they have often been dismissed as being just sort of a technical problem of, so for instance, one of these problems would be called response bias. That is, that you're not seeing something, let's say, and then you're externally or internally saying, oh, I don't see a thing, I don't see a thing, I don't see a thing, I don't see a thing. And if the evidence for the detection is really weak, that then you're uncertain. And if you're uncertain, you just keep making the same response. You are biased to what you just previously decided. And the same would work in the reverse direction. If you already see something, it would be like mentally making that response decision all the time. And in uncertainty, you would keep your response. So that's an empirical issue of how to not fall victim to that. There's a second sort of problem where you could think, well, I'm basing my response not on my current stimulus, but on just the like a low pass filter, so the recent past history of stimulation. And therefore, you would predict that if you increase stimulus, you're deciding only when there has been more suprathreshold stimuli that lead to suprathreshold activation than earlier values that had subthreshold activation. And when you come from the top, you lose the perception only when that ratio changes, and therefore that would lead to some kind of hysteresis phenomena. These things can not be excluded 100%, but I'll show you some evidence against that. These thoughts and histories was sort of caused by perception irrelevant factors have entered psychophysical practice. For instance, people will make an ascending series where they change the parameter in one direction and a descending series, and then average these two to determine the threshold. That's a standard procedure in psychophysics to get rid of what is then called response bias. So that's based on the assumption that the dependence on the previous response or the current state is not real. It's just a question of the readout system. I wanted to take you through one example that's actually old work I did with a psychophysicist, Howard Tuck, with whom I'm still working. I'll show you some very recent results that are actually not even published yet from his lab that speaks to that. And this is a case where there is very clean evidence. It's really where we've overcome a lot of these conceptual issues. So the first example, historically older, but actually a little bit more complex than the second example, is called generalized apparent motion. You're all familiar with apparent motion because you all watch videos and movies and so on, and you know that sequences of still images can generate the impression of motion if the timing and the spatial extent is right. So for instance, in the movie, you will see a contrast pattern, and then on the next image, you see a slightly shifted contrast pattern. And if the amount of shift and the time that is between two frames is about right, then you will actually not perceive these discrete shifts, but you will see actually motion of the contour. The old movies in the 19th century had too much time elapsing between the screens, and because of that, with fast motion, the motion moving contours moving too far on the visual array between two views, it was sometimes sort of jerky, and you were actually more seeing like abrupt shifts, while current rates actually hasn't changed for the last 50 years or so. We're all using the same rates now. At these rates of, let's say, 50 hertz, even like 30 hertz is enough. And the typical spatial resolution that we have in our media today, you see very smooth motion. In fact, motion you cannot distinguish as an observer from physically continuous motion. And there's probably no one anymore who claims that there will be a difference between seeing real motion and video-based motion representations. In fact, in the work with Howard Tuck, we've actually developed an argument that so-called real motion, when the motion signal is continuous, is neurally represented as this discrete so-called apparent motion, because there is some form of excitation inhibition alternation, so that you're not actually open all the time to see contrast. And so your nervous system would actually create some kind of discrete sampling in time of the underlying psychophysical dimension of the, let's say, contrast or luminance or whatever it is that you're looking at. And so it's more like apparent motion. So this is called apparent motion. It goes back to the German Gestalt psychologists who thought that this was really very important, because for them, this fact that a sequence of discrete images could be perceived as motion was evidence that the motion happens in your mind or in your brain. It's not out there in the world. This would be a case where out there in the world, there is a discrete sequence of pictures. And then you perceiving this as motion, it's you. It's an achievement of your nervous system. I actually still think of that as a very good metaphor for this to make this point. So that's been studied a lot. Going back to previous 2 centuries ago, actually now, from current point of view. So it happened sort of around the beginning of the 20th century that this was studied very well. Most of the work on perception of motion and the onset of perception of motion in this paradigm was about varying the spatial-temporal relationships to make the motion smooth. So, for instance, you could make the time of presentation or the interval between presentations smaller. You could make the distance over which objects seem to jump smaller. And if both are small enough, you see smooth motion. But it's very difficult to assess whether you're actively detecting the motion and then stabilizing that detection, because the quality of the motion would also vary. It becomes smoother as the sampling rate goes down, or goes up, the rate goes up, or the time interval goes down, and in the reverse direction becomes less smooth. And so it's difficult as an observer to say, now this is good, this is really motion, and this isn't. You could say, well, this is really good motion, and this is a little less good, and this is very jerky, oh, and this is just a sequence of images. So we were very interested in the generalized apparent motion paradigm when that came up. It originally comes from someone called Johansson in Sweden, who studied this for other reasons, and we were able to harness this for our purposes. So in apparent generalized apparent motion, you do have these discrete frames. So for instance, this would be a frame that you would be presenting at one moment in time, and this would be a frame you would be presenting at another moment in time. And think of these as happening at the same location. So I'm saying this picture here at that location is swapped out for this one. So what you will see is that the bright thing moves here. And then if you periodically repeat this, the bright square seems to go back and forth. That will be your motion. So it's generalized because the target where the motion goes also has some contrast. And when, in the reverse direction, so when this is moved, there is something remaining behind where the object moved away from. So in this generalized apparent motion, the element of detecting a new or the component of motion perception where something new appears somewhere, where there's no contrast here. Let's say regular apparent motion would be just a bright spot. There's nothing here on the right. And then on the next frame, there's only a bright spot here on the right side and nothing on the left, right? There will be just some bright spot jumping to a new location. And you would be seeing that bright spot jumping around. And that's where you could wonder whether the motion is really about detecting that new contrast at the new location and then constructing in your mind that it must be the other one that has moved there, where it previously was. That would be jerky kind of motion, that you would have to have some criterion. When is it considered to be good motion? When is it just a sequence of events of something jumping around? Now here in generalized apparent motion, you can separate these detection events from the motion events, because there is some contrast both where you're coming from and where you're going to, always. And so what's added on top is really a motion percept. And it turns out that there is a really sharp onset, sharp in the sense of psychophysically real. Naive observers will think that something changed in your percept when you perceive the bright thing to move to the new location, rather than you see some flicker, just some contrast change. And you can manipulate the onset of motion now through parameters that are totally independent of space and time, and therefore of the quality of the motion. And one of those is the so-called background relative luminance contrast. So what you do, you see, you have three relevant levels of contrast. You have the high level of contrast, the bright spot, the low level of contrast, here the darker spot, and the background contrast, which is here the gray. And from the background, you could compute the average luminance, so the average between the first frame and the second frame. And you could see that now it matters how much change of luminance you have. That is here, this amplitude, compared to how much contrast there is overall. That you could measure by, for instance, how much this average luminance differs from background. And in turn, that is what is called BRLC, the background relative luminance contrast. So it's the amount of change of contrast compared to how different from background these two elements are. When you vary that, you can actually vary the motion strength. So the most extreme case is when one of the luminance levels are equal to background. That's when you would have a bright spot on a gray or black background. That's the strongest motion signal. And the other limit would be when the difference in luminance level between frames is minimal, there's almost no change and pretty good contrast at both locations. then that would be largely a stationary signal. So let me just see a little bit of flickering. And so this doesn't affect the timing, right? It's just the luminance levels. And when you vary this parameter, you can go from no motion to very good motion and back without changing anything about the quality of the motion itself. And so that turns out to be a very good platform for detecting hysteresis. And here is a result from a sort of a culmination of many studies in which we finally nailed that aspect. So this combines this background relative luminance contrast manipulation for motion detection with something that we call the modified method of limits, that I'll explain in a moment. So what you see is that there are different levels here of that BRLC. At high levels, you're very likely to see motion. At low levels, would be a very, very tiny level in luminance variation and good contrast at both locations, you don't see motion. And so when you show something like that and you ask people, did you see motion? Most people will say, I don't. And when you show something like this, pretty large levels of percentage of people will be saying, or on trials will be saying, I see motion. So now you could say, I'm going to increase in time gradually the background relative luminance contrast, and then I should see the onset of motion occurring at a higher level of contrast than when I come from seeing motion and ask people to report when they lose motion. Now, there could still be this uncertainty. You could think, well, somewhere here in the middle, maybe they're not so clear on whether they see motion, and then they will have this response bias of just saying the same thing over and again. Even though it does turn out phenomenologically that people have a pretty clear percept when they have a percept of motion here. But to minimize that aspect, what you can also do is not ask people to report all the time. They see the stimulus, they can just watch it. And it abruptly ends at some level of this BRLC. And they only need to report what they saw last, what was the last percept they had. Now, of course, you can't be 100% sure that they're not like mentally trying to respond all the time, but you can wear them down by doing enough trials. And when you vary the depth of this, the end comes surprising, so they don't really know when they have to pay attention. So over time, this kind of strategy can be minimized. So in this modified method of limits, you would start always with a level of background relative luminance where you have overwhelmingly, with most probability, one of the two percepts. So for instance, if you start here at this lower end, almost everyone will have no motion percept, and you increase it in time, stepwise, to a level that you vary randomly from trial to trial. So sometimes it will be very short series, sometimes it will be a larger series, and you stop abruptly asking what they saw last. In fact, can vary the question that you ask. In some cases, in these cases, you're just asking, was there a switch? In other cases, you can ask them, what did you see last? Sometimes you can ask multiple questions like, did you see something? Did you see no motion, and then see motion, and so on. So this is the case where you're just asking if there's any switch. And because you make sure that initially they always have the same percept, the switch means a switch to motion. And that's how these ascending curve data were derived. And similarly, if you start with a high level of BRLC, people will almost always see motion, and you're decreasing this to a randomly chosen end level, and then ask them, was there any switch over the initial percept? And that will be a switch from motion to non-motion. And with that technique, we were able to establish hysteresis. So it's a big effort to really nail that down. That was published in 2010. So it's really late if you think of that as an old subject in psychophysics. There are very interesting subtleties about that have to do with a selective adaptation that I will not really go deeply into. I just want to hint at that a little bit. So there is a counter process to hysteresis, which is the buildup of inhibition. It's called in visual psychophysics selective adaptation, which is known. Many of you might know that after seeing a stimulus of a certain strength, you tend to lose it, and you need to have an increased input to have it again. it's also called habituation in other contexts. So you need stronger and stronger stimulus to get the same result. So become less sensitive to a stimulus. And you can think of that as a build-up of inhibition. So if that's the case, then that will predict anti-hysteresis. That is, if you're here coming up, you're in a regime where you've always, no, let's say if you're up here, you're in a regime where you've always seen motion. And so you would need more and more strength of input to keep seeing motion. And that would mean that you would lose motion earlier than if you're coming from here where you haven't seen motion a lot. So your motion detectors have not built up a lot of inhibition. And therefore, you could easily switch to that. And you can actually demonstrate the effect of such things by, for instance, spending different amounts of time here in the early phase. So for instance, if you repeat this level of contrast several times, then this whole curve moves to the right. That is, then you lose the percept earlier. So observing hysteresis actually means there is more hysteresis than this sort of selective adaptation. And that is actually the case for motion perception. We manipulated that and we established that. Now, the subtlety about that is that you could think of, well, you have neurons in the brain that represent motion, and then it's natural that they would have selective adaptation. So if you expose people a lot to these conditions, then the boundary here would move to the right. You lose motion earlier. But what about not seeing motion? Do you have neurons that are firing when they don't see motion? That's not so obvious, right? Because these neurons would everywhere in the visual array, you're exciting non-motion neurons when you don't see motion. This makes no sense, right? So it must be something else, like seeing these flickering dots of light that are not really good motion, that could then adapt and could explain the effect. And we did actually see selective adaptation on the ascending trials. And that has led to a lot of other studies, and we're still not totally finished with the research that establishes what exactly that other system is, some kind of stationary system. And that's how we actually were led to ask the question that I will show you some very recent results of. This is ongoing work where Attractors, no longer very young, is still pursuing these with his students. So this next simpler thing is, in fact, the simplest perceptual act that you could think of is just detecting a little piece of contrast. You're staring at a computer screen, and there's a little probe. This would be here, this light gray bar, and you have to say if you see it. In one variant of the experiment, you have the space bar on your computer will, for instance, decrease the luminance of this gray bar, and you would look at this display, and every time you see the probe, you would press the space bar and get a weaker gray bar, and keep doing that until you lose it. And then we can look at what level of luminance you lost the probe, and that will be your critical threshold that you need. So this would always coming from above the hysteresis. And to do this more precisely, we have a control. First I have to say, there are a couple of problems with just doing that for a single object, just a single probe, one of which is attention. So if you don't know where on the screen this thing arises, then you get a lot of variability, because it might just be a question of where you happen to look. So a simple way to make this exact is to have what we call little markers, or little object that stays on and is well above threshold. Here, this little bright spot, and then you know it's going to be, you even know in experiments by instruction that it's going to be on the right of that mark, that the probe appears if there is a probe. In fact, in these experiments, the marker and the probe jump around on the screen, only within something that would be largely the foveal region, which helps against other kinds of effects, like purely peripheral effects, just like the retina and retinal bleeding, and so this marker helps with that. But it has other, psychophysicists are very precise about these things. It has other implications that I'll gloss over here. Now, it turns out that this marker plays a role. So if this marker is more than just minimal, for instance, is an object of the same overall size and area, it actually affects the detection of the probe. One way to see that is you could compare how bright does the probe have to be in the presence of an object compared to just the presence of this minimal marker. This is what we call the baseline decision when there's this marker. And it turns out that if there's an object present, you need more luminance to detect the probe. So there is some form of inhibition from this nearby object onto the detection of a little piece of contrast. That's this distance between the baseline plotted here separately that explains that, or that displays that actually inhibition. We would say it's an inhibitory influence or something that prevents detection from the object. For instance, you can see that it depends on the distance of the objects. If they're a few arc minutes from each other, then you have inhibition. It peters out near about 20 arc minutes or so, which is related to receptive fields in the human brain, by the way. It's actually something that happens also across polarity. A black object also has an influence like that on a bright object, brighter than background, darker than background, brighter than background also works. Interesting differences between these two. And it has all kinds of subtle effects. And in fact, we're studying this because we're looking for excitatory and inhibitory interaction. There is actually some subtle form of excitation that I'm not going into, but this would be the inhibitory influence of the neighboring probe. Now, this helps us do hysteresis of contrast detection, because when you want to do a hysteresis experiment of that nature, you need to be get rid of all these attention problems, and you have a real problem of coming from bottom up. What does it mean to first detect an object? Well, with a probe, with the object present, you've already solved the problem of having some kind of attentional effect, and we can actually leverage the inhibition, because it will be very hard on a real computer screen to find luminance levels where you don't see anything, because those who construct computer screens don't want to expend bit information that isn't visible. So there's it's not like there are many levels of below threshold luminance. But what you can do is you can put up a probe and an object, and that object will suppress the detection of the probe. So now you have a couple of values for the luminance of the probe where you don't see the object. Where you don't see the probe because it's inhibited by the object. And so if for that coming from below, you have some room to have the detection come up, and then coming from above, you just lower the threshold, the luminance of the probe, as I hinted, and can look where you lose it. And this is data of that nature that's unpublished. We're just working on that. This is not even under revision. We didn't have that in the first submission. So this uses ascending trials with the luminance is increased in steps. And again, it's the modified methods of limits, that is the end luminance changes unpredictably, and you just report whether you saw a contrast in the probe location or not. And the descending trials, you decrease luminance in steps, and again, it ends unpredictably. And we arrange these, the range of these effects such that initially you either see very likely no object in the increasing sense direction, and the decreasing direction, we start at a level where you always see the object, the probe initially. So when we're asking for any switch people observed, it's a switch from seeing to not seeing, or from not seeing to seeing. And the object is close for minutes of arc away, where it suppresses the probe detection at the lowest level of luminance. That's how we can have a couple of values where there's initially a very low probability to see an object. And again, this is actually jumping around on the screen, so it's actually quite challenging to understand how exactly that happens in the brain, where it's supposed to be retinotopic. And so here we have clear evidence for hysteresis. That is a real difference between the luminance you need to first detect an object when you're increasing luminance than the level of luminance that you need to lose the percept when you already saw the object. So you lose it much later at a low level of luminance than the luminance you need to first detect it. It's amazing that it took more than 100 years to get your finger, put the finger exactly on these kind of effects. Good. So that concludes my little excursion into psychophysics to look for signatures of the simplest instability in the system that involves the simplest decision, just the detection of something. And in fact, the last stuff I just showed you is that in the simplest possible setting, just detecting a little patch of contrast, right? That's a very simple thing. We've had a lot of more data that actually shows that more complex things matter. It matters whether the object has some shape and forms some gestalt and so on. All of this plays a role, but even simple detection works like that. And so that is consistent with this notion that whenever you create a percept, and that always means you detect something, right? That there is something to perceive. There is an instability at its basis. So that perception is not transmission of feed-forward information into the network. It always involves some kind of mechanism of self-stabilization.